So we are working on determining to see whether if something is symmetric to the x-axis, the y-axis, and or origin on our graph. So to review the test, we substitute in the negative opposite variable for the x-axis and the y-axis. And if those negatives end up canceling out somehow and we end up with the same equation, that means it is symmetric to those there. If we want to see if something is symmetric to the origin, the way that we do that is substitute both a negative x and a negative y in for x and y respectively to see if we can come up with the original equation. We did an example of this in the last video. We have a couple more examples to help you prepare for your homework, which is over symmetry. So example 2 here says determine whether the graph x equals y squared is symmetric to the y-axis, x-axis, and or origin. Now I have the graph of this one here on the left, but you actually will not be able to graph this in your calculator without a little bit of manipulation. So that's why I've given you the graph. Just note on your homework you will not have that ability unless you know how to manipulate it in the right way. So hopefully at first glance you know that this guy is symmetric to the x-axis. We can fold this over the x-axis and it matches on both sides. Now, it's not symmetric to the y-axis because I cannot fold it over to the y-axis and it match. It is also not symmetric to the origin because I cannot rotate it one halfway around my circle and it be the same. So we want to confirm that it is symmetric to the x-axis but nothing else using our test. I'm going to start with my first one here. To confirm that it is not symmetric to my y-axis, I plug in negative x into my equation. So negative x is equal to y squared. If I can do anything to simplify, I would, but I can't. I cannot do anything with that negative, so that means I have altered my equation because I had a negative there. So that means this is no, it's not symmetric to my y-axis, which we knew by looking at the picture. Let's move on to the x-axis. We test for symmetry of that by substituting in negative y for y. So x equals a negative y squared instead of my original y here. Well, we know that if we were to square anything, it would always end up to be a positive number. If we take a positive number and square it, it's positive. If we take a negative number and square it, it's positive. So in this case, the square eliminates my negative. I don't need this negative here. I know that that's always just going to simplify to be a y squared. I still need to keep the square because I still have to square it, but I know that's going to be positive in the end, so I can eliminate my negative there. My x just copy down from the next step. Notice I end up with the same equation that I had before, so that tells us that this is, yes, it is symmetric to the x-axis, which we knew by looking at this graph here. All right, the origin, we substitute in a negative x for my x value and a negative y for my y value. Now we know that the square is going to eliminate the negative on my y value, but we know we cannot do anything extra to eliminate the negative off of my x value. So this is what we end up with. It is not the same as my original equation because I have that extra negative there. So that tells us that it is not symmetric to the origin. So our answer then, as we knew from the graph, it is symmetric to the x-axis, but it is not symmetric to anything else. Let's move on to my third example. X squared plus y squared is equal to 9, and we want to determine to see whether this is symmetric to the y-axis, the x-axis, and or the origin. I suggest that you pause the video and see if you can come up with this on your own. Perhaps you remember from last section that this is actually the equation of a circle. So our formula was x minus h squared plus y minus k squared is equal to r squared. In our formula, the h value happens to be 0, and the k value happens to be 0, so that means our vertex was 0. And then our r squared is equal to 3, because 3 squared is equal to 9. So that tells us that our circle has a radius of 3. So that gives me this picture over here on the left. So we have the graph of a circle. Now, hopefully you figured out what this is symmetric to, but let's do the test before we confirm it with the picture. So, to test for the y-axis, we substitute in a negative x value into our equation. Negative x squared plus y squared is equal to 9. Just like in the last example, the square would eliminate the need for the negative, so that would give us x squared plus y squared equals 9. So that tells us that it is, in fact, symmetric to our y-axis. So that means that we can fold it over our y-axis and it be the identical version on both sides. Okay, let's test for the x-axis. We do that by substituting in a negative y for the y. So it gives me x squared plus a negative y squared is equal to 9. Well, the square takes care of the need for the negative, so that gives me x squared plus y squared is equal to 9. Notice we end up with the exact same equation, so that tells us, yes, it is also symmetric to my x-axis. So what that means is I could fold it on my x-axis and it be the same. Okay, now let's test for the origin. We know we need to substitute in a negative x for our x and a negative y for our y. In both cases, the squares take care of the negative, leaving me with the exact same equation. So that says it's a yes, it's symmetric to the origin as well. So if I were to pick one point on the circle, and if I were to rotate it halfway around the circle, that means that I would have the exact same point on the opposite side. So this is symmetric to all my y-axis and my x-axis and my origin. So something can be symmetric to all three things at the same time. When we come back in the next video, we're going to be doing the same thing, but we're going to be looking at them in function format. Notice that these were not in function format. They are not defined as f of x equals. So we had graphs that actually were not functions. Remember, we can determine whether these are functions or not by doing the vertical line test. So in this instance, if I were to graph a vertical line here, it would intercept my graph in more than one place. So this is not a function. The same thing in my last example, if I were to graph a vertical line, it would intercept my graph in more than one place. So it would also not be a function. So we want to figure out how do these look like when they are in function format specifically, rather than just equation format that we have here. So that's what the next video will cover.